I thought what was very special about this conference, apart from the celebration of the 50 years of the IOA, was how all of the speakers that I've heard have made such an effort to make their talk accessible to those outside of the field. And I think this is the kind of culture where we really generate new ideas and we start to have real conversations. So just congratulations to everybody. This is not me showing off my CV. The reason I wanted to put this up is because I recently became the Director of Science at the European Space Agency. And one of the things that I challenged myself with when I took up the role was how was I going to do this immensely big job on behalf of the science community while still keeping my intellect nourished. I can't read the papers that come out every day. I can't go to all the conferences. I was able to come here for 2 whole days, which is a luxury. And I think that's also why this conference was very special. But for me, what I wanted to do was go back to, just for a moment, my undergraduate days. So I'm not an IOA alumni. I'm an interloper here. Some of you will also be interlopers. I've always enjoyed when I've visited here and I've found the environment very stimulating. But I was an undergraduate at the University of Glasgow. And there are 2 things that stand out to me from that time. The first one was when Jocelyn Bell came to give a talk to our Student Astronomy Society. And I was a first-year undergraduate, and I didn't like astronomy at all. I liked physics and maths, and I didn't know what this crazy, inaccurate subject was, that if you were good to a factor of 10, it was fine. And we had lecturers who would lecture like this, and then a raise. Professor Archie Roy could draw 2 perfect spherical spheres and do all the spherical astronomy, and I just had question marks, etc. in my notes. And Jocelyn turned up and she gave this incredible talk about pulsars. And in the middle of her talk, somebody gave her a note, the discovery, the alleged discovery of the first millisecond pulsar. It turned out it wasn't, but they were subsequently discovered. And what she did there and then was she looked and she said, she did a quick calculation in her head. I don't know if Jocelyn's still here. I can't see her. And she said, it can't be possible. It would tear itself apart. And that was real life science. And then I was hooked. Then I wanted to do stellar structure and evolution. And I went and studied my equations. No more question marks in my notes. The other experience I had, and this goes back to what Martin was saying after dinner last night, was Fred Hoyle came to visit the university. He was retired by then. He came with his wife and his daughter. And I was the undergraduate student rep. And I was invited out to dinner with these illustrious professors. So I was completely in awe. I didn't speak. I just ate. And Fred's wife said to him, Hoyle, what will you eat for dinner? You pick, dear. Will you have tea? You pick, dear. He was completely switched off to the small talk. The professors were talking about the weather and the menu, and he was just completely switched off. And I asked the same question, Martin, is this what happens to scientists? Anyway, I watched in awe. And then suddenly the conversation turned to the Kobe results, which had just come out. And I challenged Martin a little bit on Fred's stubbornness on the steady state theory. Because at that point, it was as somebody had flipped a switch. And Fred suddenly talked massively animatedly about these incredible results, how the line is thicker than the error bars, and what a phenomenal experimental result this was, as you were saying, Neil. And so what I saw there was that spark of childhood curiosity. If you read his autobiography, he wandered across the Yorkshire moors. I was born in Yorkshire. You know, he was a bit of a maverick in school. He wanted to think interesting things. He didn't want to do boring things. And I think in some ways he also didn't fit in here. You know, there's all sorts of history and politics here. But that was the pure scientist. And I think if you get a moment like that in your career has been worth it. Rarely do we, because we think about grants and we think about funding and we think about whether our code works or whether it's going to destroy the planet. And I think that's why we do what we do. So I hope you have a little sense of that from this week. And I've also seen with my work in government, I'm an observational astrophysicist by background. My background is now across the electromagnetic spectrum, and I've developed and exploited ground and space-based technologies, particularly for black holes. But when I worked in government as the chief scientific advisor in the foreign ministry, I saw how powerful science diplomacy was for good. Whatever the geopolitics are of the time, whatever is happening between nations, when we come together in these international fora, I really believe anything is possible. And that was really the basis on which I was hugely honoured to be appointed first woman director of science at the European Space Agency. Not a job I could have done, I now realise, had I not had that experience in government. I am an international civil servant, and I serve our 22, now 23 member states, and ultimately the wider science community. But what I have to do is I have to get the money in. And so I need your help. So at the end of this talk, I want you to think about what are the big questions you're trying to answer. And the one thing that sticks in my mind is journalists say to me, nobody cares about your mission. Nobody cares about your code. Nobody cares about your computer. It's a euphemism for what are the big questions we're trying to answer. We have to do the detail. We have to do the due diligence. We have to do what we do in all of our daily lives. But ultimately, I have to boil this down and convince maybe transport ministers or economics ministers that this stuff matters. So what we do is a privilege, and I do think it matters, but how we articulate that is also important. And this was 2022, so our new Director General, Joseph Ashbacher, who is in the middle, brought together 22 ministers. This happens for our agency every 3 years. A minister from each of our member states comes together for a ministerial conference, and they set our budgets. We spend a lot of time working internally to put a proposal in front of our ministers, and you can imagine across those 22 countries the different kind of politics, the different kinds of ambitions, the different kinds of restrictions. This should have been a very difficult ministerial. We had the war in Ukraine, we had vast cost of living increases. But this, for me, again, is a very optimistic and hopeful picture. So if you do think you're going to go and shout at your minister, just stop for a moment and think about how you can make your case constructively. I heard you say, Carlos, that, you know, when I think Chris made his comment, we have a new government, we should go and speak to them. Come speak to me about how to speak to them over coffee. And actually, it was hugely optimistic. We got a record uplift in our budget. I mean, you know, the pressure is now on to repeat that next year. And we got a 17% uplift overall and a 13% uplift for science. 3.4 billion euro program is the one that I manage. This is the mandatory program, and so I actually have to have unanimous agreement across all 22 member states. The other programs in the agency are optimal, and it's on a subscription basis. So I have literally just traveled to each and every one of those 22 countries to understand how to get them to support my bid to uplift the budget. But underpinning all of this is world-class science. Now, this is something that you all have at the heart of what you do. You're all competitive. You're all trying to push the frontiers, but that really is the important part here. We don't do nice to have science, we don't do mediocre science, because these programs are so phenomenally competitive. Now, the other takeaway message from my 22 member state tour was that so many people think science is scientists sitting in their offices having nice thoughts. So hands up if you're a theorist that does that. Okay, maybe no. But mostly we don't. We need money, we need people, we need ideas, and we need stuff. And so the technology interface is also very important. Not technology for technology's sake, but that interface between the scientific method. This is why I keep asking the speakers, do you have a testable prediction for me, please? Because we have to use the scientific method. And it doesn't matter how beautiful our simulations are, how wonderful our detectors are, what are those frontier questions we're trying to solve? And how do we push forward that frontier of knowledge? And it's a slow frontier to push forward. I also need that commercial environment across Europe, because when I put contracts out, unlike NASA, I have capped budgets, and I do need industrial competition. So I will run contract competitions, and when I have a monopoly situation, it's very risky for our missions, because then the price can go up, and that's not something I can allow. We also have a very strong agenda on sustainability. You'll all be thinking about the dark and quiet skies. There is a tension in any space agency. On one hand, we want to launch stuff. On the other hand, that's actually bad for protecting the sustainable environment. So that's a tension. Also reinforced autonomy and sovereignty. Now, this is a European base, and it's same for any other agency. We had a launcher crisis. We're now back accessing space, but also for the science program. I think we're the only space agency in the world that doesn't have a nationalistic view. We bring 22 countries together for that wider common good. But we have to do the best we can. We have to be the best in order to be good partners with other international agencies. Nobody wants to partner with mediocre. And of course, inspiration goes without saying. So next year, the European Space Agency will celebrate its 50th anniversary, and I hope to invite you all, maybe to Madrid. And what I've done coming into the program, I have a completely different view to the view that I had from outside as a scientist. As a scientist, I knew some of the missions. I was on proposals for some of them. I didn't understand the systems at all, and it's very different once you're inside. Inside, I found this incredibly coherent, diverse program. But one of the challenges for me is that if you choose any one of these communities, you will probably only see one, maybe two missions in your lifetime. And that's not enough. And that's one of the other bases for uplifting the budget. But we now are, I think, after just 50 short years, at a very mature place. We have 3 different class missions, and not as big as NASA, but we have our large L-class Flagship missions, which are kind of 1.5 billion euros, our medium class missions about the 500 to 600 million, and then our fast fast class missions, which are around about the couple hundred million. We invent new technologies because we're pushing frontiers, and we have lots of novel design, not just in the instruments which our member states provide, the systems engineering, everything from orbital trajectories, long-term operations. So we have to be innovative on a daily basis, but these missions last for lifetimes. This was 20 years ago, and the reason I'm putting this rather than casting forward 50 years, I wanted to think back. Now, 20 years ago, ESA could not fly a major mission of its own, but we took a piggyback ride with NASA's Cassini. And we landed, a soft landing, the Huygens probe landed on Titan, which is a moon of Saturn. It's the most distant successful soft landing on a body beyond our Earth that humanity has ever achieved. And that was a real landing. And the orange haze there is just the hydrocarbon haze. We had a soft landing because we thought we would land in an ocean of methane, but actually everything's frozen. And you can see the frozen ocean or lake bed there. And if you look at this on YouTube, what's incredible is the thing bounces, then you see the shadow of the parachute going past, and then you see the camera autonomously zooming out to show you the sun. So this is the view of the sun from Saturn. We did that 20 years ago. Now imagine who had to imagine 15 years before that this was possible and pitched to the ministers. It sounds like madness, right? Insanity. 10 years ago, was the ESA Rosetta mission. So then we figured out how to do this ourselves. Again, iconic, we flew out to a comet. Comets don't have much gravity, so we had to have very innovative flight paths in order to chase the comet, orbit it, and then ultimately land on it. And it was an incredible mission, and again, it captured the public imagination. But the ingenuity to do that, this again was a 20-year baseline. It took 10 years to get there. Think of the imagination, the creativity, but the sustainability of hardcore things like your legal frameworks, your finances, your staffing, all of this. And then just coming to another solar system body, Mars, because this obviously now is on everybody's sights. Let's go colonize Mars. Let's see if there's life on Mars. Our Mars Express mission has been orbiting around Mars for the last 20 years, and we've done well to keep that going. And I remember the debates where, is there any water on Mars? Well, there is water on Mars. There's lots of water on Mars. There's a very dynamic water system on Mars. There's deep water, there's dust level water, so we know that it's a dynamic system. And most recently, we even found morning frost. So this water frost, freezes and thaws on a daily basis as the sun rises over the volcano. This is Olympus Mons. It's the biggest volcano in the solar system. So we're learning all the time. And because that mission could be sustained for at least 20 years, again, not just the engineering, the finance and everything, we've also been able now to map the surface topology of the moon Phobos, because our colleagues in Japan want to land a probe on Phobos fairly soon. And it's nice to know what you might be landing on. And so we've been doing that mapping for them. But a recent paper came out that suggested maybe Phobos and also Deimos are not moons of Mars. They may actually be Jovian comet remnants, like Comet 67P that we landed with Rosetta on. So we're having a brand new understanding of the formation and evolution of our solar system. And so across the whole of our portfolio, we have really quite a nice set of missions. On the bottom, these are legacy missions that have flown in the past. All of the data are available in the archives. In the middle, these are missions that are flying at the moment. And the ones at the top are the ones that are in preparation. We have the same for our cosmic observers. So we cover most of the electromagnetic spectrum, but you'll see that there's one mission in each pot. So when we lose integral, for example, we've lost the gamma ray sky. So again, this impetus to make sure that we can fill this. And I asked my team to do an analysis and project this into the 2040s, and I was deeply shocked to find that the sky is empty. So if we don't get an uplift in the budget in 2025, we'd have no technology preparation for missions in the 2040s and beyond. So our 50-year plan is actually dead, to be brief about it. And this, I just wanted to show you that lifetime of missions. Hubble's on the bottom, first conceptualized in 1943. It's been flying for 34 years. It's an incredible mission, still heavily oversubscribed. And over the next 13 years, we plan to launch a major space science mission from ESA every 1.5 years. And when I say we plan, I mean these are being built in the lab as we speak. Last year, just 1 month into post, I went to my very first ever rocket launch, and this was to launch our first L-class mission, which is termed JUICE, the Jupiter Icy Moons Explorer. And this is a phenomenal mission. It has 10 instruments on board, remote sensing instruments, in situ instruments, and geophysics instruments. And it's taken about 20 years to develop this mission. The idea is actually to study the Jovian system. It's like a mini solar system, so we can actually understand solar system physics by actually focusing on Jupiter. But it's also a very hostile environment. But the big question that mission wants to ask and answer is whether the icy moons of Jupiter, which we think have frozen solid crusts and below liquid salty oceans, whether those conditions could be habitable for life. We'll not land and test for life, we'll just look for the conditions of life. But the other wonderful thing about these missions, we call them kind of Christmas tree missions, we hang everything off them because they come along so infrequently, is that we can now use this mission to study planetary archetypes in the broader sense, the water worlds and gas giants, which are common among exoplanets, and use the Jovian system as a lighthouse for those. And also in that broader search for habitable worlds, what makes a world habitable and how can we do this beyond our solar system? And for those of you who don't care about planets and the solar system and it's just grit in your eye, Jupiter is also an astrophysical analog. So we have extreme particle accelerations, we have extreme magnetic fields, we have really complex astrophysical systems there, radiation mechanisms. And so our astrophysicists will also get some very useful data there. If you've never been to a rocket launch, I can recommend it. The rocket launch itself is amazing. This was an Ariane 5 rocket, similar to the one that launched Webb, and actually gave us another 10 to 15 years of lifetime because the launch was so exquisite. The same for JUICE. We had a 1-second launch window. So there's no waiting for the weather cell to go past. You launch or you don't. It was absolutely exquisite. And these were some of the selfies that the satellite took leaving Earth. So this is great for public outreach, but there's also a serious note. Now, remember Chris was mentioning GRISM. There's a little thing that's jammed and they might want to shake the spacecraft and heat it up. Yep, we did that with JUICE. So we did have this rime antenna, and it's like a folded up fishing rod, and the pin was jammed. And so for the whole of the summer after we launched, we had to heat the spacecraft a little, we had to shake it. You really don't want to do that with your first L-class mission. And we now have a policy to put cameras on all of our missions because a picture speaks 1,000 words. Obviously, we have the telemetry. This is on loop. It shows that the arm goes out, it locks in place, it doesn't recoil, we're all fine. But the movie also showed our engineers that what the telemetry was telling us was correct. So we cheered at that moment. And the other very special thing about this mission, and actually in August now, we're going to do the very first Earth-Moon gravitational assist. So our rockets are not powerful enough to go straight to Jupiter, but we will do these gravitational slingshots, a double gravitational slingshot in August between the Earth and the Moon. We'll do the same thing around Venus in August 2025, and then we'll do similar things around the Jovian system, taking data as we go. We'll finally land into orbit around Ganymede, and because of the exquisite launch, we'll be able to get down not just to 500 kilometers above the surface, but 200 kilometers above the surface of Ganymede and do an extra orbit. So any Jovian scientists here, you should be super happy. So we have a very good program. Envision is a mission that we adopted this year along with Lisa. And I know there are colleagues in the audience who have other Venus missions, but I think Venus is now very much the flavor of the next decade. This, again, is a very exciting mission. We'll have to do some aerobraking in the oxygen-rich atmosphere to get into orbit, which is a challenge because oxygen is very corrosive and you literally don't want to dissolve your spacecraft. But what this mission will do, again in collaboration with our colleagues at NASA, is study everything from the upper atmosphere right down to the core of the planet. So we will have the most complete understanding of our sister planet that has ever been achieved. And we like to do extreme things, so we know how to do these very difficult maneuvers. Bepi Colombo is a mission that we launched in 2018, and it's actually been doing this kind of braking in a different way to get into the orbit of Mercury. And this has been likened to flying into a pizza oven. It's incredibly hot, it's very challenging for our systems, and it's really pushing our engineers to the limit to get into orbit. We're hoping by 25, 26 we will be in orbit around Mercury and we will launch 2 probes. So again, you see a theme of multi-component missions coming along. This is one of our flybys, and this is real data. And again, you can see that you're actually doing real flybys of these planets. We did another one a year later. This is the high-gain antenna. And again, the scientists have useful data on each of these flybys. We like to be in hot places, clearly. Solar Orbiter is an iconic mission as well. It launched in 2020, again in this very hostile thermal environment, very close to the sun. And for the first time, we will, as a species, be coming out of the plane of the solar system, and we'll get the first views ever of the poles of the sun. So that, again, is important for our understanding of the sun as a star, but also for planetary protection. And this is just a quick clip of what the sun looks like in quiescence. Obviously, we've had amazing flares from the sun in May, but this is actually the little micro flares that we now know fuel the regular solar wind. And I think you'll see a little bit of a mini flare. So this is a second for every 5 minutes, right in the middle. You'll see a little blip in a minute. Watching paint dry. There you go. Yeah. Exquisite. And to put this in context, this is the sun on the largest scale, and on loop in the top left, that's actually Mercury transiting across the sun. That's where our satellites are. That's just to give you a context of our real-world operating environment. And I said about the solar system, understanding these interloper bodies. And again, this is a neat technology. Comet Interceptor is a little mission that will launch with our exoplanet mission Ariel. And it will go out to L2, it will loiter in deep space, and it will wait for a pristine comet from the edge of the solar system to come by. It will chase it, and it will launch 2 probes to study it. So again, we like to do nifty things. And we now think the solar system might be twice as big as we previously thought. There are plenty of those objects out there, so we think we have a pretty good chance of finding a good one to study. And again, we care about these things if they come into the inner solar system because they can do us some damage. This also is important for those of you who study extrasolar planets. How do you form these planetary forming disks? And why is our solar system twice as big as our models tell us it is? Our suite of exoplanet missions are incredibly exciting. Webb is transforming this field. Cheops is a little mission, and we've been using that to study Neptune-sized planets. But Plato will be our next big planetary mission, exoplanet mission, and it will actually study Earth-like planets around solar-type stars. Technologically, it's 26 cameras that have to be made to exquisite identical precision and integrated to make a single instrument. And that, just in terms of engineering quality control processes, is already a frontier. We'll launch that in 2026, and then in 2029, Ariel will launch, and Ariel will study the atmospheric chemistry and the climate properties of over 1,000 planets, and also the thermal properties of the sun. So you see now that, 20, 30 years ago, if you asked any astronomer, do you think you will ever be able to see a planet in another solar system? I think the answer would have been categorically no. And now we're actually doing climate change in other solar systems. So flipping quickly on for the last few minutes into cosmology, we've seen much of this morning. You've heard about Euclid, again, a beautiful launch last year. The idea is really to study dark energy and dark matter coupled together. Because of the beautiful Planck satellite results, we know the cosmic microwave background and the temperature fluctuations and how they seed the sorts of things we're now seeing with Webb. But what Euclid will do is quite special, and it's also built on some new technology. We have a huge reputation in Europe for astrometric missions, Hipparcos, Gaia, Euclid. And one of the other things that we've developed is this material called silicon carbide. And it's very difficult to grow it, but we've developed this technique in Europe from Herschel all the way up. It's structurally very stiff, and it's thermally very stable, which is exactly what we needed for Euclid, because we've now got these very, very sensitive infrared and optical cameras and spectrographs on this combined platform. We have a little bit of ice on the visual camera, and the thickness of that ice is less than a strand of DNA, and we care about that because our cameras are so sensitive. It's a big telescope. We launched it on a Falcon 9, and we had to do some special work with SpaceX to make sure that that was stable. It was a beautiful launch. And what Euclid is special for is something that I think most optical astronomers can only ever dream of. So you've heard the old adage in computing, cheap, fast, reliable, choose 2. Well, in optical astronomy, you can have field of view, resolution, or sensitivity, choose 2. Euclid now has delivered 3. So that's the Hubble Deep Field. In a single shot with Euclid, we cover 2.5 times the size of the full moon on the sky, 600 megapixels. We've got exquisite sensitivity and angular resolution, and over the next 6.5 years, we will cover the entire extragalactic sky out to 10 billion years. The rest of it is filled with the Milky Way and the zodiacal light, which we've done with Gaia. And I apologize to theorists who do beautiful simulations. This is just one I picked out. I haven't picked it for any particular reason other than to show filaments. And also to really pay tribute to ground-based astronomers over many, many years who have painstakingly done galaxy surveys and redshift surveys. This is the Sloan, but 2DF preceded this. And all of that painstaking work now is in the middle of what Euclid will do. And this is what we hope to answer, obviously. What's the rest of the 95% of the universe? And there are some very subtle things that the cosmologists will have to do because, of course, dark matter and dark energy are coupled. And we also want to understand the gravity on cosmological timescales. I love this little clip. You'll all understand this, but this was from my colleague Mark McCaughrean to try to describe to politicians how gravitational lensing worked. Because people keep saying to me with Euclid images, where's the dark matter? Show me the dark energy. And I think, how do I show you what you can't see? So this is very sweet. In the middle, you can imagine that the base of the stem of the glass is the matter concentration at the center of a galaxy cluster, big distortion. At the edges, a little distortion. And you see that, the big distortions here in a nice web image. You can put a galaxy image there, you can distort it. What we're looking for, of course, is the weak lensing and the cosmic shear, which are intimately coupled. And for that, we absolutely need precision images. I've shown this because I thought it was great that Neil showed this. We didn't confer on our talks these acoustic peaks, but of course, the baryonic acoustic oscillations make a spatial imprint in 3D. So around about 360 to 380,000 years after the Big Bang, so redshift of 11,000, although I can't get there with my spectroscopy, I can get the code of it. And because we can do such big patches on the sky, we can now look for these alignments, these baryonic acoustic rings. But these are not rings, these are actually spheres in redshift space as well. And in fact, the very first one was published recently by Brent Tully and his group. So we may have found one, and then obviously Euclid will find many, many more of these. We released some early images, some ERO images in November. I just thought I'd zoom into these. This is a dwarf galaxy. You can zoom in here. That's a little Eta Carina star formation region. And this is why I asked the question about star clusters. These are all over the Euclid data. I've only looked at a few images. They're literally everywhere. Globular clusters, star-forming clusters. We've got an exquisite resolution and coverage. This is a galaxy cluster, and I literally just took the image out, and I've started to zoom in. I haven't done any animation here. There are thousands and thousands and thousands of background galaxies, and you can get very close to the bright sources as well. We've got the intracluster light, and we can actually trace the dynamics of globular clusters in galaxy clusters now with Euclid. So it's absolutely mind-boggling, and our politicians gave us a round of applause for this at our political summit in May. The data processing is a challenge, so Volker, please come speak to me. Maybe we can bring the theory and put it next to the data and put a combined case in. We're spread across 9 data centers, 8 in Europe, 1 in the US. As somebody mentioned, 2,500 scientists, 2,000 industrial personnel. We'll look at 8 billion galaxies. We'll pick 1.5 billion of them for the cosmology. Mission cost about 1.4 billion euros, so it's about 90 cents a galaxy, so I think that's pretty good value for money. I want to mention Gaia. I'm looking at Jerry here, but we've already prototyped how to do this kind of groundbreaking data analysis and serve the community. And again, you know, real credit to the Gaia collaboration. That's not a photograph, that's a dot-to-dot picture. Every single pixel in that is a star. We know its properties, we know their types, we know where they've come from, we know where they're going, and therefore we know the formation and evolution history of the Milky Way. And you can see this pink salmon slice here in the publications. Gaia has literally blown every other mission out of the water, including Hubble. And really, that's not just because of the Milky Way science, it's because there's so much other science, ancillary science that other communities are being able to do. Whether that's background quasars, this is the most complete sample yet, just extracted out of those Gaia data. Whether it's looking for lensed, strongly lensed quasars to do cosmology, again, a different axis of cosmology. And again, a huge amount of work here on the machine learning and the typing to go from 3 million, 4 million quasars down to 49 strong lenses. I mean, that's a real piece of work. And then, of course, discovering black holes in our Milky Way galaxy. Not the central supermassive black hole, but stellar mass black holes. And it will be the kinds of things that merge to produce this that we'll use as our cosmological calibration sources for the first couple of years of LISA, which we currently just have out now to industrial contract. Again, phenomenal technology, 3 spacecraft that have to be identical, flying 2.5 million kilometers apart to a precision of smaller than a proton. And they will fly and they will sense ripples in space-time, providing that we get the engineering right, and the test mass on each of those spacecraft don't know they're on a spacecraft. Again, huge international collaboration, real testament to European leadership and with our friends at NASA. I wanted to finish with a hot universe because Chris Reynolds mentioned this. We have 2 missions of opportunity that we worked on for launch this year, GRISM with the Japanese, and Einstein probe, which is a transient X-ray mission looking for gamma ray bursts. And as Chris showed, we're now in the realm of doing proper X-ray spectroscopy, which is very exciting. New Athena is back on the table. Chris, I'm sorry, it's going to probably stay new. But as a colleague pointed out to me, New College, Oxford was founded in 1379. And it kept its name, so don't get too hung up on the name. Phenomenal technology. This is going to be the X-ray observatory of the 2030s. All of the data are available in our archives, and we continue to renovate the tools that you can use cross-mission. So if you're a planetary scientist and you want to get something out of a cosmology mission, I had one archive scientist who came and said, I can find all the metal asteroids in the Planck data. Wow, who knew? And we also have mission data, so you can start to take the engineering data and you can start to do science, things like cosmic ray science with the engineering data. I'm sorry, just 1 minute into coffee, because the technology program is really important, and I want you all to think about the technology that enables your science. I've mentioned the silicon carbide, which started with the mirrors, the solar panels, 85 square meters, unfurled like butterfly wings in orbit for JUICE, and the silicon pore optics for New Athena, which, if you ask me over coffee, I'll tell you why that's so special. It's not just stacks of silicon, it's a whole engineering process at scale. And also we help our member states with the payloads, because they provide the instruments and we give them lots of help with that. There's a huge amount of innovation in those instruments, and we also put funding into that for them. So lots of innovation, not just in the science program. And then finally, my big job, apart from getting the uplift, or the reason for the uplift, is really the long-term strategy. So back in 2019, we did a thing similar to the decadal review. We asked all of our scientific community to come with ideas. We received 100 white papers, and we had an expert science committee that worked for 2 years to boil these down to themes. And we came up with these 3 big themes for our next L-class missions, which I hope to launch once a decade. That's about the right cadence. I was told that there were 14 world-leading feasible proposals for these L missions, and our teams had to boil those down to 3 themes. So the first one, we already know what we'll do for L4, and then we have 2 others. We also will hope to have a series of M-class missions. We already have 3 M-class missions in down select. They're in study phase at the moment, the M7s, and we have our little galactic archaeologist, Arrakis. And just to finish, the next L-class mission, our L4 mission, will be to seek life on icy moons and water worlds. It will build on everything I've shown you, landing on comets, chasing comets, going around Jupiter. And we've done a 2-year scientific and technical design study, and our scientific community said Enceladus is the best place to go to seek life in the solar system. But you can't just go and orbit around it. You can't just fly through the plume. You've got to land. So we now have an embryonic design. We will launch on 2 rockets. We will have a spacecraft. We will do in-orbit assembly. We will use electric propulsion to take us to Saturn. We will do a tour of the moon system. We will fly through the plume, and then we will land, and we will do about a month's campaign seeking life on Enceladus. And I have only 10 years from this minute, and I have no money yet, to do all of the technology development, all of the miniaturization, because it's not just cost, it's mass budget as well, in order to adopt the mission in 2034, because we have to launch in 2043 to get to Enceladus in 2052, when the South Pole is pointing at the sun. So that's how we do long term. And I hope that we inspire next generations, because we're going to need the next generations, because I also want to retire at some point. Public engagement, people love these missions, and it's for all of you to help me make that case in the broadest and deepest sense. And I hope that with your ideas, with your voice in a coordinated way, through ESA and with our international partners, we'll be able to make this magic triangle and really have a really hopeful and productive scientific future for the next 50 years. Thank you.